this generating function. So characteristic function, I did not cover this. So the last few slides I did not cover. So in the exam, I will not give big problem, this sort of problem. So probability generating function also, I did not cover. And Python, we have been doing computer assignment using Python. Okay, so that concludes chapter number 4. Now we are starting chapter 5. That is the last chapter in part 1 of our course material. Our course, the title of our course is Probability, Statistics, Random Processes, 3 parts. So one part is the probability, the other part is the statistics, and the third part is random processes for electrical engineering. So chapter 1 through chapter 5 is part 1, which is probability. Chapter 7, we skip chapter 6 because it will take attention of chapter 5. So we skip chapter 6. So chapter 7, 8 is going to be, these 2 chapters will be on statistics, and chapter 9, 10 will be random processes for electrical engineering. But those chapters I will be covering a few sections, so those chapters I will be finishing. It will not take much time. But fundamentals from chapter 1 through chapter 5, I didn't want to compromise, so that's why it took a long time for us to complete the first part of our course material. So chapter 5 is about pairs of random variables. So in chapter 3, we talked about one discrete random variable. In chapter 3, we talked about one discrete random variable. Random variable that is discrete, and we just dealt with one random variable. Chapter 4, we dealt with one continuous random variable. So only one random variable, but that was mainly we dealt with one continuous random variable. Chapter 5 is going to be based on the theory that we covered in chapter 3 and chapter 4 on one random variable, but we are going to extend to 2 random variables. So you're getting more practical scenario, 2 random variables. So this is the main idea. You will see like I drew, I don't plan on modifying chapter 5 slides because over the break I actually drew all the figures and worked out all the examples. So chapter 5 is ready to go. So I uploaded all the chapter 5 slides, and you can just annotate my slides as we go. So we'll talk about 2 random variables, and these 2 random variables could be discrete or continuous. Discrete or continuous random variables. So which actually makes sense, because in real world we just do not have one random quantity. We have many random quantities. If you talk about a robot, like a humanoid robot, for example, a humanoid robot has 200, 300 degrees of freedom with many different models, and each model gives you position information, and those position information, those are random. Okay, so as you can see, 2 or 3 degrees of freedom or 300 degrees of freedom, all these are random variables. So in practical scenario, in real world scenario, we just don't get only one random variable. We covered one random variable as part of the basics, as part of the fundamentals, so that you know. So now we are moving on to 2 random variables. And then chapter 6 is about n random variables, n number of random variables. It's just the extension of chapter 5. So we will be covering chapter 5 in detail. So in two random variables, we, again, because we are covering probability, therefore there will be a sample space, and sample space is basically a set of outcomes, and each outcome should map to these vector random variables. So this is called vector. I'm going to use red. This is called vector random variable. Vector random variable, which means that this random variable consists of two quantities, two random variables. So that's why this is bold. You just note that right from here. This is bold, uppercase. Uppercase, that's the notation for vector random variable. Any linear algebra book that you see, any linear algebra book, okay? So they use this notation. Lowercase bold letter to represent vector, uppercase bold letter to represent matrices, okay? And other quantities they use special symbol, Greek symbol. But when you see bold symbols, which means that those are vector quantities, vector or matrix quantities. Now here I have uppercase, but still it is vector, just to denote that this is a vector random variable, not only a deterministic vector, it is a random variable. That's the notation. So each outcome actually maps to a point in two-dimensional space. Why two-dimensional space? Because it's a vector of two random variables. One dimension we have one random variable, other dimension we have another random variable. So that's why it is R2 space, which means that it can go from negative, this x1 can go from negative infinity to positive infinity, and x2 can range from negative infinity to positive infinity. So that's why it's R2 space, two-dimensional space. Again, because we are working with two random variables, that's why we have this R2. If we work with three random variables, it's going to be three-dimensional space. If we work with four random variables, four-dimensional space, and so on. You guys got it? So, why it is important? It is important when we talk about this joint, we talk about two random variables or n random variables, because we want to determine the joint behavior. How these two random variables behave together, jointly. How these two random variables behave jointly. So we want to describe their joint behavior through joint PMF, probability mass function. We went through probability mass function for this one discrete random variable. We went through CDF, cumulative distribution function. But this time, instead of simply PMF CDF, we say it is joint PMF, it is joint CDF, and it is joint PDF. When we talk about two continuous random variables. Joint probability density function, joint cumulative distribution function, and joint probability mass function. We would also be talking about describing average behavior through joint moments. So we talked about moments, first moment, second moment, third moment. We talked about that for single variable. But here, because we are talking about two random variables in this chapter, so we will be mainly talking about joint moments and expected values to describe the average behavior of a random vector that consists of two random variables for the moment. We will also talk about another statistical parameter called correlation. Correlation coefficient in this chapter. So these are the terms that you will see down the line, like once you pursue advanced studies in statistics, probability statistics, random processes, or stochastic processes. These are the terms that you will come up with. You will know, and therefore this is the fundamental chapter where you are getting introduced by this terminology, correlation. Correlation basically it's dependence of one random variable on another random variable, how they are dependent, how they are correlated. So I have some graphic, I have some plots that I'm going to show in a moment, so that you know practically what these correlation means. Also, conditional probabilities involving one variable given the other. So this conditional probability will omit this. Will omit this conditional probability because we will mainly focus on the fundamentals. Then conditional probabilities basically will be using Bayes' rule, which we covered already. Okay, so here you have some other notations. Author has denoted this vector random variable with a comma like this. So this is a vector random variable that takes outcome as an argument, and author has denoted with this one. So x as a function of outcome, comma, y as a function of outcome. So between parentheses, it's basically the same, but in my slide, in my notes, I will be using this column vector to represent vector. Okay. So that is the difference. Please don't get confused when you study the textbook. It's basically the same. Only thing is that my notation is different. Here, I use this column vector to denote the vector. Okay. So this is a random vector that takes outcome from the sample space as the argument, and it maps to real space in two dimension. So when you see this vector, which is an element in two-dimensional space. So I just repeated the previous figure here. So outcome, each outcome maps to this through this random vector and points to maps to a point in two-dimensional space. So this is x, this is y. So it's going to be actually y as a function of z. All right. Now let's talk about event. Okay. So we talked about a single outcome. Now talk about event. Okay. Event in sample space identified with this letter A, which is basically a bunch of outcomes from the sample space. And when this event gets mapped, this event is mapped to another event on this two-dimensional space, how do they do that? So it maps to, each outcome maps to each point in two-dimensional space. And then if you circle or if you draw the region, you will see you have another event B. And this event B is basically on real space, two-dimensional space, and event A is in sample space. So please make sure you distinguish this notation. So event B is in random variable space, here it is two-dimensional space, and event A is basically in sample space. So event A and event B are equivalent through this relation, where event A can be determined from the inverse relationship, which means that each point in B can be mapped back to the sample space. So that way you can actually determine what is the event A in sample space from event B in two-dimensional space. So this is just the notation. Here, look, here you have x as a function of zeta, y as a function of zeta, as which is basically an element in B, which is this space. So you can just think of each point basically a number. So 0.25, 0.5, 0.96. So each point you can think of this number, and each of these points can be mapped to this sample space. But we will be mainly working with this random vector, which basically deals with numbers. So we have one example, and I gave you the solution as well. You don't have to write with me. I gave you the solution, but I'm not going to read this solution. So what it says that each of you in my class, okay, each student, okay, you can think of this. I can just pick any student from you. Okay, I pick any student from you, and I want to that any student, basically student name, for example, zeta is an outcome. Okay, but how this outcome maps to two different quantities. One is height. His height is different than his height. Okay, so one outcome maps to two different quantities, height and weight. So height of student zeta in centimeters and weight of student zeta in kilograms. So your outcome maps to two different quantities, H, W. Two different quantities. So HW is a random variable. So height is a function of zeta, because this zeta is a student. So student's height will be different. Each student's height will be different. So that's why it's a random variable. It's a very simple example just to show you that how each outcome maps to two different quantities. And it can map to many different quantities. So when I create homework assignment, I'm going to give some examples. So I'm going to include these examples when I create the homework assignment. Now, how we can see these events in two-dimensional space physically? Okay, visually, how we can actually see these events. So these events, I could use Python to draw these figures, but I drew these figures using LaTeX just to match with this color information. In Python, I cannot control color like this, and in Python, I cannot actually give arrow and different symbols like that. One event here is A is x plus y less than or equal to 10. You can actually see this shaded area. This event corresponds to this shaded area, where you can see any point in this event, if x plus y, any point x, y, so x coordinate plus y coordinates, you will see that this is going to be less than or equal to 10, because this coordinate is 10, 0, and this coordinate is 0, 10. So any coordinate here, you'll see, any point here, you will see the coordinates, x coordinate from y and y coordinate, if you add them up, it's going to be less than 10. This event mean x, y less than or equals 5. What this event physically visually represent, see, it is this area. It is this area. This is your 5, 5. So minimum of x coordinate. So here, let's say it's going to be x equals 2 and y equals xy is going to be 2. For example, here 7. So minimum of 2, 7 is going to be 2. So you just pick any point, you pass through this mean function, you will see that it is going, this point belongs to this event. So that's why I actually shaded this area. So this is your event B. And event C, visually, how does it look? Event C is x squared plus y squared less than or equals 100. In other words, it's x squared plus y squared less than or equals 10 squared. Where 10 is the radius, it's a basically circular region, 10 is the radius. Radius r equals 10. So this area, you can see that this is your event C. So any point here, any point you see, any point here, we have x coordinate and y coordinate, x, y, x coordinate and y coordinate, you will see x squared plus y squared less. Any point here, you will see that this condition is satisfied. So these are all theory. Now let's move on to another direction where you actually plot the sample measurements for two different random variables. Here we have two different random variable x, random variable y. So this is, you plot, this is x-axis, this is y-axis. You have random variable x, random variable y, and then you take one sample, one measurement of x and y, and you plot it. So, and as you can see, these samples, x, y coordinate, these are completely uncorrelated. And we will actually know, we will actually see how we define this correlation, correlation coefficient, and this correlation coefficient is going to be negative 1 to positive 1. We will see all these correlation towards the end of this chapter, correlation theory towards the end of this chapter. So these are uncorrelated, scattered, and these are basically points towards the center. So you can see the joint behavior. And here you can see joint behavior, kind of circular shapes, but still these are uncorrelated. And here you see that these points are strongly correlated. And, there is another term called positive correlation and negative. Positive, if I ask you positive or negative. Okay, if I ask you, just, we don't know what is correlation, we do not know the theory behind it, we do not know anything about correlation then. But just by looking at this sample data, sample measurement, can you say these are positively correlated or negatively correlated? Yes.
I think it's positively correlated.
Yes.
It looks like y.
Exactly, exactly. So positively, what it means practically is if x goes up, y will also go up. If x goes down, y will also go down. Negative correlation, negatively correlated, this data will be this way. Which means that if x goes up, y will go down. Okay? So that's what negative correlation means. And we will, these quantitative measurements of correlation, we will learn this towards the end of this chapter. But here, initially, I plotted just to highlight the concept, the idea, how these random variables are correlated, how do they behave jointly. So I actually described each of these plots right here. I'm not going to read my slide. So what I just said that they are nicely written in the following slide. What is important here is that scatter plots help visualize the joint distribution of two random variables and provide insight into their dependence, spread, and correlation. All right, now we are going to gradually, move towards computing probability of events that consist of two random variables. How to compute the probability? Okay. So math is not hard at all. Like you will understand. Only thing is that this notation that you will have to understand. Okay. What it means in two-dimensional space, just to understand the notation, guys. In two-dimensional space, so this is your y, this is your X, and then let's say this is the event. This is the event B. Okay, this is the event B. Now, this portion is your set A1, and this portion is your set A2. This is A1, this is A2. This part A2 is from y-axis, A1 is from x-axis. That's the notation. So random variable x can take any value from this set A1. Random variable y can take any value from this set A2. And this gap means this is AND operator. This gap means this is AND operator. So the event here is that random variable can take any value from this set A1. A1 could be this set, and A2 from and random variable y can take any value from this A2. Now the product form, probability of product forms, you write it like that. So probability that random variable x can take any value from A1, y can take, and y can take any value from A2. So this is your AND. So that's how you get the joint behavior. That's the ultimate goal. So you determine the joint behavior of these two variables. What is the probability? For example, what is the probability that you two guys had height less than or equals 6 foot, for example, or less than that, or more than that, 6 foot. Okay, so we will determine that probability. Okay, but this probability, given the fact that we have these outcomes, random experiments are properly defined, but in chapter 7, again, from now on, I'm going to begin. In chapter 7, we will absolutely have no idea about the probability of random experiment. All what we have is just bunch of raw data, and based on raw data, we will determine this what it is. Okay. So, but so far we do not have this raw data. So we define the random experiment. Therefore, we will be able to determine this probability. So, what is the probability that a random variable x can take any value from this range in x-axis, and random variable y, and keyword is and here, and random variable y can take any value from here. So we have that, and I tried to visually draw this event B. So this is this event B, x1 less than x less than or equals x2. So this is x1, x2, and this is and gap or intersection. We learned in chapter 2, y less than or equals 2. So y, you have the upper limit y. So therefore, the event that you see, event B that you see, is basically this area. This area is your event B. Here, this event is basically rectangular event. This is a rectangular event. You see that x1 less than or equals x less than x2, y1 less than or equals y less than or equals y2. But because these are continuous random variables, guys, again, these are continuous random variables, this less than or equals or simply less than doesn't matter. Because probability that x can take exactly the same value, exactly equal to a certain number of steps. So that's why less than or equals or strictly less than is the same thing. For continuous random variable, you can do that. Other type of event is this. So you have random variable x can take any value greater than x1. So that's why this number can increase here, but in the negative direction. That's why you have x greater than x1, and y has bound. So this is y2, this is y1. So y values are bounded, but x values are bounded from certain area. So that's why this is your event B. So you have different types of events. So that's how you actually visually know how event B is represented. Now, to compute the probability of what we do, because we said that in a random experiment is properly defined, we first define the joint range. Oh, I did not write. Okay. S, we have been denoting S as range of random variable x, right? You remember, guys? S sub x is basically range of random variable x. S sub x comma y is, we are going to call it joint range. S sub x comma y, we are going to call it joint range. Okay? So joint range in countable set, let's say a sample space, you have discrete sample space. So joint range, we denote it with like a coordinate x sub j, y sub k, where j can take any value from 1 to 3 because of the discrete random variables, and k can take any value from 1 to 3 because of the discrete random variables. Now, joint probability mass function for discrete random experiment, for random experiment that gives a discrete outcome for two different random variables. So joint probability mass function, we write it as such. So probability, guys, listen here. So that's how you read it. Joint probability mass function of random variable x comma y taking values x, y. So that's how you read it, guys. So joint PMF probability mass function of random variables x comma y taking values lowercase x comma y equals probability that x equals x and and y equals y. Do you need this notation, guys? What is this? Equal and then have a triangle. So this is basically called equal by definition. Equal by definition. So the difference between this line and this line is that see and, you know, you have to write like and, it's a cap symbol. So in short, for convenience, people write it comma. When you see comma, which means this is and. Is that clear? When you see comma, x equals x, and I remove this curly bracket, just to simplify. Okay? For convenience, people write it x equals x, comma, x equals y. For x, comma, y, taking values from the two-dimensional real space. In case you have countable outcomes, xj, yj, it's basically the same thing. So you just write x equals xj, y equals yj. Now, from the sample space, if you know, from the sample space, if B consists of bunch of points xj, comma, yk, okay, so this is going to go on the homework problems. Xj, comma, yk, and let's say I'm going to define the set like this. So j equals 1 to dotted dotted, and k equals 1 to dotted dotted. Okay. So if you have bunch of points, so point here is that what is the probability? How to compute the probability? So how to compute the probability? If you know the joint PMF, you can actually compute the probability as such. So probably that's how you write. Probability that the random vector takes value from the set B is basically you take summation. So instead of single summation, you have two double summation. Not two different summation. You have double summation. One summation is over J, and the other summation is over K. So so you make summation, but if you see that event B maps to the entire sample space, then the joint range will here I should write joint range. Joint range x, y, then for all values of x, j, y, j, like because you are taking the entire sample space, if you make double summation, it is going to be simply 1. So these are all the formulas. With these formulas in mind, we are going to move on to our first example in today's lecture on packet switch in a server, in a packet switch system. So we are going to solve our first example. So in the book, guys, it's very confusing example. Make sure you pay attention. I drew as much figures as possible over the break. So we will actually cover this example in the second half of our lecture. So you will have 5 minutes break.